Okay, so today we're going to transition to three-dimensional lines now, still using the same vector notations we saw in 2 dimensions. So the vector equation, the basics look exactly as they did, and as we tried to stress when we moved from vectors in 2 dimensions in the first place to 3 dimensions, the same sort of rules that will apply here. Nothing's really going to change. We're going to add it in the 3rd dimension, but other than that, there's not too much different. And so obviously in this case, this is the vector to a specific point on the line. This is a direction vector. We want to recognize that it just happens that this is the point I know. Of course, my vector equation for this exact same line could have a different point here. I could use a different direction vector, -3, -2, 6, or 6, 4, 12. Any multiple of this vector, and that's what the t means, any multiple of this vector gives me a direction vector as well. So in the same way that this could be 2 times this, I could have 8 times this or anything else. And so all those numbers could be different as long as they're a multiple of what we already started with. Now extending that out exactly again as we did yesterday, we will also have symmetric and parametric equations. Symmetric equations here, basically we will, sorry, I guess we should do this in the other order. The parametric equations first. If we want to remember that our x value is determined by the x value of the 2 vectors being added together. And so again, 0 here plus 3t's. The y value is established by taking the -4 and adding 2t, and z is 8 plus 6t. The parametric equation, you can see this format is the nicest for finding points, because basically if I'm asked to find 1 point on the line, I can put a value in for t, 1, 1, and 1, and I find that 0 plus 3, -4 plus 2, and 8 plus 6 is another point. So what was that? 3, -2, 14 is a point on the line. Putting in any common value for t gets me an x, y, and a z that work together that are another point on the line. We certainly can still find points in other formats, but this is sort of the nicest one for that specifically. If we rearrange these then and solve for t, we get our symmetric equations. And of course, symmetric implies that they are symmetrical, meaning that each one is equal to the others. And so we're simply isolating the t in each case, and we rewrite it this way. And then just a quick little note, I sort of suggested it already. None of the forms above give unique solutions. Okay, so anytime we write an equation now, once we're into 3 dimensions especially, but even with the vector equations in 2 dimensions, again, this is established, or this form of the equation is established given a specific point on the line. So any other point on the line could also have been plugged in here. The direction doesn't necessarily change, but it can be rewritten as well. And so when we're saying none of the forms above give unique solutions, it means that everybody in the class could come up with a different correct vector equation for a line just by having different points and using different multiples of the direction vector here. Now a couple little things come up, sort of specific things I want to mention. If we had looked at this and had a different direction vector, now this may not be the exact same example, this is out of the textbook, but the point is still the same. So if our direction vector were 2, 4, 0, when we go about writing our parametric equations, we get x equals this. Again, sort of this was the point in the example and in the book, not too important for what we want to get through here. The key, of course, is the z. Z is just the number 3. We get that, or 0, sorry, the equation for z is just z equals 3. And the equation for that is basically because of the multiplying by 0, we have 3 plus 0t, or z is just 3. Because of that, we can't really write this as a symmetric equation. So if we just sort of think about what we would do when we rearrange this equation, or what we would try to do is rearrange this equation, we would subtract z minus 3, and then of course we would divide through by the 0. to get our t-value. And clearly this is something we can't do because of the division by 0. Okay, so that's sort of what this explains here. And so if you are asked to write the symmetric equation, or if you are trying to write the symmetric equations for for a vector that has a 0 value, that has this sort of a situation, this is how we write it. So the first two parts are symmetrical, and then comma, and just repeat the parametric equation for the third value. Okay, so just sort of establishing that's what you may see at times, and if not, that's what you will do when you run into that situation. Now, if we are asked to determine whether two lines are parallel, one of the things I meant to mention, sort of when we look back at the three different forms of our equation here, you should be able to see, and you probably did see last day, that the actual numbers in all three forms of the equation are always the same. 0, -4, 8 was a point in the vector equation. That's how we start. And so when we look at the parametric equations, here is the 0, -4, 8. And so that's a point from our line. When we look over here, it's maybe not quite as clear, but here's a +4, here's a -8, and so what we've actually got here is y minus the -4, z minus +8, sorry, that should be a nice round bracket there, and this is x minus the 0. So if we do have the symmetric equation and we're looking for a point, it is kind of there as well. Certainly this is a nicer way to see it. This is fine once you make the association, but it is here as well. The point is the subtracted value across the numerators. The direction vector, of course, a little bit easier to see. I see a 3, 2, 6, I see a 3, 2, 6, and I see a 3, 2, 6. So all that said, just kind of getting back to where we were going here, show that the lines are parallel. Of course, if the lines are parallel, the direction vectors will be scalar multiples of one another. And so based on what we just said, this is the direction vector for line 1. 1, 2, -3. In this case, -2, -4, and 6. And so I've just sort of said that I'm going to let m be the direction vector for the first equation. Maybe m1 would have been smarter. m2 is the direction vector for the second equation. And so if they are parallel, then m can be written as a scalar multiple of m2. And so really what you're doing then is you're asking, is there a k value, is there a constant value by which I can multiply 1 to get this value over here? If it's fairly obvious, as it is in this case, we can simply work it out. If it's not quite as obvious, we have some other options. One would be to write the equation, or write it as several little equations. 1 equals k times -2, and solve for k, and then do the same thing basically for the other values. 2 equals k times -4, solve for k. If, of course, you get the same k value in all three cases, actually that's what I did down here, I didn't sort of realize that's what I was doing, then you end up with the same constant, and of course they are parallel. Okay, so as soon as we can come up with a single k value by which each of these multiply to give us each of these, we know that the two lines are parallel. And sort of this is the thought process. The math works, of course, in reverse, in that the k value would be 1 divided by the -2 in this case. And if we do the same thing for all three x, y, and z values, then we should get the same k value if in fact they are parallel. So all of that leads us to the granddaddy of them all, though the intersection point of two straight lines in 3 space. So this is example 3 out of the text, or out of the file that I gave you. Here's my line 1, here's line 2, and show that the lines intersect, determine the coordinates of the point. So the first thing is sort of just a quick little note here. Now that we have a third dimension, we do have the possibility of having another possible outcome. When we dealt with straight lines in 2 dimensions, and certainly in grade 9, you did 2 lines could be parallel, they could cross at a single point, and they could be the exact same line just written differently. So we sort of had three possibilities there. We do have a fourth possibility now, and that's just that they are what we call skew, which means essentially the one line just kind of misses the others. I'm sorry, one line misses the other one. So it's hard to draw it, but if you think about it in 3 dimensions, we could have a line that's kind of way up here on our graph and kind of going in this general direction. We could have another line that's much below it and going this way, so that although they pass over each other, or one passes under the other, there's a huge gap between them. This one's way up in space, maybe up crossing through like a Z value of 21. This one has all Z values down in the negative area. Clearly they would then, when they crossed, they'd pass by each other but not actually intersect. So just think of it as, if you hold a ruler up, can somebody stick a ruler underneath you, underneath that one that doesn't actually make contact with it? And of course, it's very easy to do in 3 dimensions. So what's the process we're going to go through? First thing, check that the 2 lines are parallel is probably your best bet. There's not a lot of reason to go through the process of trying to find the point of intersection if in fact it doesn't exist, because it is a lengthy process. So in this case, I look at 1, -2, 4, exactly as I did last time, and ask, is there a k value by which I could multiply to get these numbers? And that doesn't look like there is. So now I've eliminated the ability for the lines to be parallel. I've also eliminated the ability for them to be the exact same line, because of course the exact same line will at least be parallel, but it'll have some more possibilities as well. So started off by rewriting as parametric equations. And then essentially what we want to recognize is, for a point of intersection, what point of intersection means is that the x's are the same, the y's are the same, and the z's are the same. So in this case, x1 is equal to x2, y1 equal to y2, z1 equal to z2. And that's what we're trying to determine. So we isolate the x's, we isolate the y's, the x, y, z's, and the x, y, z's. And then what we'll do, or what we have now, is knowing that the x1, y1, and z1 over here, knowing that x1 should be equal to x2, y1 equal to y2, and z1 equal to z2, we actually make those equations equal. Okay, so one key, I guess I didn't hit on it, but it should be pretty obvious. I've used t here as the scalar value to multiply in the first case. In the second case, if I'm rewriting it, I want to make sure I use something different. There's no reason to assume that the number t that represents this one and what would have been my t over here would be the same. So again, a t1 and t2 is fine, but really it's just some scalar number, and so s here is perfectly fine as well. Now, once I've got my equation set up, x1 equal to x2, y1 equal to y2, and z1 equal to z2, I've got 3 equations with only 2 unknowns, and I can use 2 of them to solve, again, exactly as I did in, I guess it was grade 9 as well, when we started doing systems of equations. Solve for s and t with 2 of the equations, and then we want to verify them in the third. If it does verify, then we've found our point of intersection. If it doesn't verify, then it means that we have a sort of a different situation, or we made a mistake, of course. So just continuing, this is the exact same question still. I'm choosing this as my equation 1, this is equation 2, and I won't go through this. It should be fairly obvious. Using substitution or elimination or something. In this case, I've isolated the s value, it looks like, and I subbed it into the other equation. Solve for t, solve for s, and then test them. This is sort of where we will pick up again. We're going to test those values in equation 3, because equation 3 has not been used yet. There is always a solution for 2 equations, 2 unknowns. Well, that was probably inappropriate to say. There will be a solution for two equations with two unknowns at this point because I've already verified that we don't have parallel and we don't have the same line. What we have to determine though is, did the solution for those two equations also work in the third one? And so subbing the -1 into the left side, so into 4t plus 5, I get a value of 1. Subbing the s into the right side, I get a value of 1. And again, this is just sort of that kind of mathematical form. If I don't know for sure that two things are equal, I will not write them as being equal. And so the left side I do know is equal to this, the right side is equal to this. When I substitute the values in, I'm still not making stuff up, I'm not lying. If I write down 4 times 1, or 4 times -1 plus 5 equals -3 plus 4, technically I don't know that to be true and I shouldn't be writing it. So this is just proper form for verifying. And, oh, sorry, yes. So we got 1 and 1, which means that the t value and the s value I calculated are correct. And so now I can go through the last step, which is actually figuring out what the point is. I'll plug the -1 in for t, and I get the point. X value is 2, y value -5, z value 1. Just in case, I can check it in the other one. When I plug the 3 in for s, I get a 2, a -5, and a 1 again. And so that is my point of intersection. Of course, if you get to the point now where we can't solve this, because we've already eliminated the possibility of it being parallel lines, which means we've technically already eliminated the possibility of it being the same line. If we can't find the point of intersection, what we're left with then is, when we do our testing here, we get values that don't match up, and we recognize that we must therefore have skew lines, because really we've gone through the other possibilities already.